Today we are talking about rational function properties, new unit, dealing with rational functions. You guys are going to be able to analyze rational functions. We will get to graphing them and we will get to solving rational functions as well, or rational equations. So we're going to do the whole gambit, and this is going to be the focus of this particular unit. It's a small unit, it's a short unit. So you know, this probably will take us into Christmas. Maybe you can stop a little bit earlier. We'll just have to see how you guys handle the information. So to start, a rational function f of x is the quotient of two polynomial functions, a of x and b of x, where b is a non-zero, okay? Quotient, what does quotient mean? What's another word for quotient?
The result from dividing.
It's the result from dividing. So essentially what you're doing is you're dividing one polynomial by another polynomial, okay? And we talked about polynomial functions. That was like the entire last unit. The one thing is though is that bottom polynomial cannot be zero, okay? Now the domain of a rational function is going to be the set of all real numbers excluding those values for which b of x is equal to zero. Well, b of x is the denominator of that rational function. And as you know, we cannot divide anything by zero. That's why the domain is all real numbers except that value, okay? So an example of a rational function would be something like f of x is equal to x minus 3 over 2x plus 1. This would be an example of a rational function, okay? You have one polynomial, x minus 3, divided by another polynomial, 2x plus 1, okay? Not to be confused by something like this, okay? 2x plus 1 over 3, that's not a polynomial function, okay? It's a linear function, because this is the same thing as saying 2 over 3x plus 1 over 3, and this is not a rational function. It's a linear function, okay? So it has to be essentially something involving an x on the top and something involving an x on the bottom, okay? Or, actually, let me kind of correct that statement that I just said if you guys were listening. Let me apologize. That is an example of a rational function, okay? You do have your denominator that consists of a variable and something else. That would be an example of a rational function as well, okay? So you actually could have a number divided by an expression, but not the other way around. So yes to these, but not to that one, okay? All right, the reciprocal function is the most simplest of the rational functions that we have, okay? The reciprocal function is 1 over x. That is your most basic parent function. That is also the parent function where all of the transformations would occur, okay? Not on this yet. Stop writing this down. I'm not there. Stay with me, okay? 1 over x is your most simplest rational function. This is where all the transformations happen to them, such as if you move left or right. That is what affects, that's how you move left or right with a rational function, okay? Your most simplest rational function, which is the reciprocal function, moving left or right. Or if I move up or down. Or if I have a vertical stretch or shrink. Or if I have a horizontal stretch or shrink. Okay, the most basic, most simplest rational function, that reciprocal function, is also the one that has all the different types of transformations that apply to them as well. Okay, we talked about transformations a while ago. They do also apply to these functions as well. Okay, so just to make sure you guys haven't forgotten that, remember this is your moving of left or right. Remember, it's always the opposite. So if it's a minus a number, what does that mean? It moves to the right, okay? Again, this means up or down. Here, anything that's attached to the x, that is your horizontal stretches or compressions. We'll say stretch or shrink, and then this one would be your vertical. Okay, so those are the different types of transformations that can apply to a reciprocal function. Okay, any questions on that before we get into the different types? Now, each rational function has different types of asymptotes. These are lines that the graph will approach. They are vertical asymptotes, horizontal asymptotes, or slant or oblique asymptotes. Okay? We've talked about asymptotes before. We have. When we talked about discontinuities, we talked about vertical asymptotes. What was another name for a vertical asymptote?
Infinite?
It was an infinite discontinuity, okay? It was an infinite discontinuity. These were those dotted vertical lines. That's where the function was undefined, okay? Now, with a rational function, you're either going to have a horizontal or a slant or oblique asymptote. You're not going to have both. You're going to have one or the other, okay? And a horizontal asymptote is what you guys probably imagine it to be. It is a horizontal line. Slant asymptote is going to be one that actually forms a diagonal type of a line. Oblique is going to be the kind that form a particular shape, maybe like a quadratic or something like that, okay? So you're either going to have a horizontal or you're going to have a slant or oblique asymptote. Again, those are lines that the graph will either cross or touch. Talking them specifically though, vertical asymptote, that occurs at the real zeros of b of x. Remember, b of x was the denominator of your rational function, okay? So wherever the denominator equals 0, those are going to be your vertical asymptotes. So if you have a rational function such as n of x equals x over x squared plus x minus 2, and you're asked to find the vertical asymptotes of this particular function, well, you want to find the zeros of your denominator. So that means you want to set your denominator equal to 0. To solve a quadratic, you want to factor. More than likely, I'm talking about 99% of the time, it's going to be factorable, okay? So to factor this, I'm looking for two numbers that what?
Add -2. Multiply -2, add to 1.
Multiply to -2 and add to give you 1. So multiply to give you your C value, the last number, your constant, and add together to give you your B value. What two numbers multiply to give you -2 that add together to give you 1?
Negative 1 and 2.
2 and -1, -1 and 2. So you'll have x plus 2, x minus 1 is equal to 0. And then just like before when we were solving quadratics, we just set each factor equal to 0. And what we'll end up getting are our vertical asymptotes for this rational function. So in this particular case, you're going to have two vertical asymptotes. One at x equals -2 and the other one at x equals 1. Vertical asymptotes, they are equations. So you must have x equals if we're talking about vertical asymptotes, okay? There is a difference between vertical and horizontal and slant asymptotes. That's why it's important that you distinguish. X equals are for vertical asymptotes. And again, the domain of a rational function is all real numbers except where the denominator is equal to 0. So the process of finding your vertical asymptotes also tells you what your domain is of the function as well, okay? So our domain for this particular rational function is going to be the set of x values such that x cannot equal -2 and x cannot equal 1. But x is an element of all real numbers. So again, all real numbers except where the denominator is going to be equal to 0 because it'll be undefined there. So x cannot equal -2, x cannot equal 1, x is the set of all real numbers. This over here in the red is the domain of this particular rational function. Questions? How would I write this in interval notation? All real numbers except -2 and +1. How would I write that in interval notation?
Wouldn't it be, oh, sorry.
You can go, Anna.
Okay, wouldn't it be parentheses, -infinity, comma, -2, parentheses, union, -2, comma, 1, parentheses, union, 1, comma, infinity.
Very good. In your homework, when I ask you to write your domain of these rational functions, you'll be writing in interval notation. So you want to make sure that you're able to do as such. Okay. Your next type of asymptote, which are your horizontal asymptotes, you want to look at the degree of A of x and B of x. That is of your numerator and the denominator of your rational function. Okay, there are these few stipulations. Stay along with me. Let's try not to jump ahead, okay? First off, let's review this terminology. We talked about what a degree is in the last unit. What's another word for degree?
Power.
The power.
Power.
More specifically, you want the largest power, okay, of your numerator and your denominator. Because once you look at the degree of your top and your bottom, if the numerator is less than your denominator, then your horizontal asymptote is y equals 0 every single time. Okay? An example of that would be something like 1 over x, your most simplest rational function. The degree of your numerator is 0. The degree of your denominator is 1. Oh, yes. And so the numerator is less than your denominator, so then it'll be y equals 0. But if your numerator is equal to your denominator, then your horizontal asymptote is y equals c. And c is the ratio of the leading coefficients of the numerator and denominator. More terminology, leading coefficient. What is that?
The coefficient of the variable with the highest degree.
It's the coefficient of the variable with the highest degree. So if you have a rational function that's like 2x minus 2 and then 3x plus 1, here the degrees are equal. You have a degree of 1 and then you have a degree of 1 for the top and the bottom. Since they're equal, the horizontal asymptote is going to be the ratio of the leading coefficients of the numerator and denominator, which would be 2 and 3. So in this case, your horizontal asymptote will be y equals 2/3. Okay? Just like how this one would be y equals 0, the one in the orange would be y equals 2/3. If the numerator is greater than the denominator, again, we're talking about the degree, the exponent, that power of your top and your bottom. If the numerator is greater than your denominator, there is no horizontal asymptote, but it's slant or oblique. To find those, you would have to use synthetic division or long division, which we will talk about long division in the next class, okay? But essentially you would have to divide literally the numerator by the denominator and get the equation, and that would be your slant or your oblique asymptote, okay? Slant is the synthetic, oblique is your long. And again, we'll talk about long division on Wednesday, so you won't have any obliques yet. It's just slant, okay? Let's practice some, okay? I think flip over on the back, right? Or actually it's a completely different page. So if you want to, you can separate them so you can have your notes side by side, okay? Remember, when you're finding a horizontal asymptote, you have to look at the what?
Degree.
You gotta look at the degree.
Degrees.
You gotta look at the degree, okay? So let's see, who's been paying attention? Who has been paying attention? Luke, what's the degree of the numerator in A? What's the degree of the numerator in A? Talia, I got you. Think you might need some assistance. Scott, can you help him out?
The degree for the numerator is 0.
It is going to be 0. There's no variable here, right? So that meant that it had to have been a 0. So the degree is 0 here. Online, Brandon, what's the degree of the denominator?
Zero.
Not 0. What is that exponent that's right here attached to that x?
One maybe. I'm not sure.
It is 1. It is 1. Because think about it, if it was 0, it wouldn't be there like how it was in the numerator. But because we had an x there, the degree, the exponent is a 1. So we got to compare them. The numerator is what to the denominator, Sydney? It's less than. So because the numerator is less than the denominator, that means my horizontal asymptote is going to be
Y equals 0.
and it's going to be y equals 0. Make sure you include that y. So anytime the degree of the top is smaller than the degree on the bottom, it's always y equals 0. It's always y equals 0. Let's look at B. 15x plus 3 over x plus 5. Natalie, what's the degree of the numerator?
1.
It is 1. And Thais, what's the degree of the denominator? Still on? Thais, are you still there? Maybe not. Ryan, what's the degree of the denominator?
1.
It is 1. So in this case, the numerator is blank, the denominator is equal.
It is equal.
So when it's equal, that means it's going to be y equals what? C, and C is the ratio of the leading coefficient. So what's my answer?
15.
15 over 1, which would just be 15. So y equals 15. That means you have a horizontal asymptote of y equals 15. When I look at C, x squared minus 7x plus 10 over x minus 3. Simon, what's the degree of my numerator?
2.
It is 2. And then Jada, what's the degree of my denominator?
1.
It's 1. So in this case, the numerator is blank the denominator. It's greater. When it's greater, do we have a horizontal asymptote?
No.
So there's no horizontal asymptote, but there is a slant one. So to find the slant asymptote, what you do is you do synthetic division. We did synthetic division a lot in the last unit, okay? I am trying to divide x squared minus 7x plus 10 by x minus 3. I can do synthetic division here because I do have that linear factor as my denominator. So I take the 0, which is going to be the opposite of the denominator. And then I take the coefficients of my numerator. That's 1, -7, and 10. Hopefully you guys haven't forgotten this over break. When I do synthetic division, I bring down the first term. Then I multiply. 3 times 1 is?
3.
Then I add. -7 plus 3 is? Then I multiply. -4 times 3 is? 10 minus 12 is? -2 represents my remainder. When you're doing the asymptotes, your slant asymptotes or your oblique asymptotes, you're not going to be concerned about the remainder. You want this part right here. That ends up being your slant asymptote. And if you recall, when we divide, we always decrease 1 from the power. So this ends up becoming 1x minus 4, or just x minus 4. And that is our slant asymptote. It's an actual line with a slope and a y-intercept. Okay? But that is how you find your slant asymptotes. You use long synthetic division to do so.
If you just put x minus 4, that would also be the same, or does that one have to be there?
That one does not have to be there, but you do need to have the y equals. Because y'all are talking about a slant asymptote, so it has to have that y equals part. Other questions? A lot of information today. We will practice everything after we get through the last little bit, okay? We got x-intercepts, y-intercepts, and holes to talk about. To find an x-intercept, it hasn't changed. Just because we're in a rational function, you set technically you set your function equal to 0, but it's the same thing as basically setting your numerator equal to 0. Your a of x equal to 0. To find your y-intercepts, you plug in 0 for x. That hasn't changed, it's the exact same, okay? So when you have to find your x and y-intercepts of your rational functions, again, to find your x-intercept, you set your numerator equal to 0. Well, in this case, of n of x equals 2 divided by x squared plus 4x minus 3, my numerator is 2. When I said 2 equal to 0, is that possible? No, it's not. So because it's not possible, there is no x-intercept. It can happen. The graph cannot cross the x-axis. It can happen. But then to find my y-intercept, I plug in 0 for all of my x's. So find my y-intercept, I plug in 0 for all of my x's. So then that's going to be 2 over -3. So my y-intercept is a point, 0, comma, -2 over 3. Doesn't matter that the denominator is negative, it makes the entire fraction negative. So I have no x-intercept for a, but I do have a y-intercept of -2 over 3. Let's check out B. I have x over x squared plus x minus 2. Again, I can find my x-intercept by doing what? I set the numerator equal to 0. So that's going to be x is equal to 0. I don't have to solve anything out. I'm good to go. I'm done. I just have to actually write it as a coordinate. That's going to be 0, 0. You know, when you have an x-intercept, your y-coordinate is 0, so it's 0, 0. And then, of course, my y-intercept, you probably already guessed what it's going to be. If my x-intercept is 0, 0, my y-intercept is going to be 0, 0 as well. But just to make sure I run this into the ground, you plug in 0 for all of your x's to find your y-intercept. You'll get 0 over 2. 0 over anything is always 0. So you have a y-intercept and 0, 0. Questions?
Would it be a -2 or would it be a +2? Like, do you add it over or is it? Okay, I'm just making sure.
It'll be a negative. I did forget about it. But that's easy stuff. Y'all been doing that since grade math or 7th grade math, whenever you first learn it. Wholes, though, they're a different beast, okay? The reason why is because students forget about wholes, okay? When the numerator and denominator have common factors, the graph of the function has a removable discontinuity, also called a whole. We talked about those, okay? You have infinite discontinuities, which are your asymptotes, your vertical asymptotes. Then you also have removable discontinuities, which are your wholes, okay? So to find your whole is a coordinate, okay? To find it, you want to simplify the top and simplify the bottom. You do that by factoring the top and the bottom, okay? So if I were to factor the top, I'm looking for two numbers that multiply to give me 24, that add together to give me 10. 6 and 4. So when I factor my numerator, that becomes x plus 6 and x plus 4. I need to do the exact same thing for my denominator. I'm looking for two numbers that multiply to give me negative 12, add together to give me 1. So that gives me x minus 3 and x plus 4. A good rule of thumb when you are working with rational functions is you are going to want to factor the top and the bottom if they can be factored, okay? Because as you can see, by factoring the top and factoring the bottom, we have a common factor, and it's x plus 4. Wherever there is a common factor, and I think I've talked about this before, but whenever there's a common factor, that is where the whole occurs, okay? So I'm technically just left with x plus 6 over x minus 3, and I have a whole at the point which I need to find. You find the x coordinate of your whole by setting the common factor equal to 0, okay? I'll say that again. I find the x coordinate of my whole by setting my common factor equal to 0. So when I solve, what do I get? Negative 4. That is the x coordinate of my whole. I find the y coordinate of my whole by plugging in the x value to the simplified form. The simplified form, which is right over here in the orange. That's how you find the y coordinate of your whole. You don't want to plug it back into the original because what you're going to end up having is 0 over 0, which means it can be simplified. You want to plug it into the simplified form. So when I plug negative 4 in for x into the simplified form over here that's boxed in black and written in orange, that's going to give me 2 over negative 7. So my y coordinate is negative 2 over 7. And that is how we find the whole of a rational function. I'll recap. A whole occurs when the numerator and denominator have a common factor. You can find this common factor by factoring the top and the bottom and seeing what cancels out. The x coordinate of your whole is when you set that common factor equal to 0 and you solve. You find the y coordinate by plugging in that x value into the simplified form. Okay? The one thing you do not want to do, or the one thing that you cannot have, is you cannot have a vertical asymptote where you also have a whole. Okay? Look at this problem one more time. We find vertical asymptotes by setting the denominator equal to 0. But if there is a whole at one of those factors, then you cannot have a vertical asymptote there either. So with that being said, find your whole before you find your vertical asymptote. Because if you have a whole, then that value is the whole. Whatever's left over is your vertical asymptote. So here, there's a vertical asymptote at x equals 3, because I set whatever was left over in the denominator equal to 0 to find that vertical asymptote. Say it one more time for the people who didn't hear me in the back. You cannot have a vertical asymptote where you have a hole. So find your hole first, then find your vertical asymptote. You find your hole by factoring, and whatever the common factor is, you cancel it out. And when you set that common factor equal to 0, and do all the stuff to find the coordinate, and then whatever's left over in the denominator, you set that equal to 0, and that is your vertical asymptote. And those are all the properties of your rational functions. So all the properties of your rational functions. Let's put it all together, okay? This is not on any notes. I just want to make sure that everybody is understanding how to find everything, okay? So we're going to find the domain, the holes, vertical asymptotes, horizontal asymptotes, or oblique slant asymptotes, y-intercepts and x-intercepts. And to be honest, that's kind of the order you should think of as well. That should be like the order you think of as well. Find the domain first, holes, and then so on and so forth. I'll do this one with you. Then I'm going to give you one to try on your own. First thing, to find our domain. Our domain is everywhere where the denominator b of x does not equal 0. So that means I need to do what? Of the
denominator.
I can say not equal to, because everywhere it is not equal. How do I solve this?
Add the 9 over.
I can do it 2 ways. I can factor this, set them equal to 0, because it's a difference of perfect squares, or I can add the 9 over, and then take the square root. The only thing about when you add the 9 over, please remember, when you take the square root, you have to remember what?
You get the plus and the minus.
The plus and the minus. So my domain is all real numbers except where x equals +3 and -3. So I can write that in set notation pretty easily. I just have to add in the rest of the goods.
When we write it in set notation, can we put plus or minus?
You just put plus, minus, like side by side. Or you can write it in interval notation. That will be -infinity to -3. Not included because it's undefined there. Union -3 to 3, because everything in between -3 and 3. Union 3 to infinity. No brackets, because it's not defined at -3 and +3 nor at infinity. In B, let's find our holes. How do you find your holes? Factor the top and the bottom, see what cancels out. How does the top factor?
X minus 3 times x plus 4.
How does the bottom factor?
X plus 3 and x minus 3.
So this difference of perfect squares. Do I have anything in common?
X minus 3.
Sure do. So if something's in common, that means I do have a hole. Okay? And remember, we have a hole at a coordinate. You take that cancel out factor and you set it equal to 0. What do you get? 3. And I find the y coordinate by plugging that 3 into the simplified form of the rational function, which was x plus 4, x plus 3. I'll plug that x value in.
6.
So it'll be 7/6. So I have a whole at 7/6. Okay. Once you find that simplified form, that x plus 4 over x plus 3, you can use that for the rest of the problem. Okay? You can, and you'll get the exact same answers as if you were to use the original problem. Okay? So to find your vertical asymptote, what would I need to do? Set the denominator equal to 0. So when I solve that, x will equal, and remember it's the full equation, the x equals as well. That's your vertical asymptote. Very good. Am I going to have a horizontal asymptote here? Or is it going to be a slant asymptote? How do I know?
Because of
Aren't they equal? The degree is equal, so just be C.
It actually is going to be a horizontal asymptote because the degrees are equal. Remember, we got to look at the degree at the top, degree at the bottom. If they're equal, which they are, whether it was the simplified form or the original, they are both equal. So because the numerator is equal to the denominator, it's going to be y equals
C.
and which will be 1. So if we have a horizontal asymptote, that means we will have no slant or oblique asymptote. How do I find my y-intercept?
Plug 0 in for x.
Plug 0 in for x. I can plug it into the simplified form or I can plug it into the original. I'll still get the same answer. I'm going to use that simplified form though to make it a lot easier for myself. That's going to be what? Four over 3. It is a point, so it's going to be 0, 4 over 3. And how do I find my x-intercept?
You plug in 0 to the numerator. Or you set the numerator equal to 0.
I set the numerator equal to 0. And I am, again, take that simplified form because remember, there was a hole that occurred. You don't want to set x minus 3 equal to 0 as well because that's a hole there, not an x-intercept. So that's going to be x is equal to -4. So my x-intercept is -4, 0. That's putting it all together to get all the different features of this rational function. Same directions, new function. Try this one on your own. Domain, holes, vertical asymptote, horizontal asymptote, oblique or slant ones. Y-intercepts, x-intercepts for this function. X squared minus x minus 2 over x minus 1. I'm going to try to find the domain of this function. Okay? Try to find the domain of this function. Remember, that's everywhere where the denominator doesn't equal 0. Who has the domain? Just gonna waste this.
Parenthesis, negative infinity, comma, 1, parenthesis, u thing, parenthesis, 1, comma, infinity, parenthesis.
Very good. Yes. You take the denominator, where the denominator does not equal 0. When you solve that, it's everywhere except where x is equal to +1. So yes, that's exactly how you write it in interval notation. Perfect. What about the holes?
There are none.
There are none?
None.
How did the top factor?
X minus 2 is x plus 1.
Ah, yes. There were no holes. No holes. Good stuff. Somebody online, tell me the vertical asymptote.
X equals 1.
X equals 1. Very good. You set the denominator equal to 0, and it's x equals 1. Okay? How you find it? Did I have a horizontal asymptote here?
No.
No.
No. So that must have meant that I had a slant one then. Yeah? Okay. What'd you get?
Y equals x.
Y equals x? Let's double check this. Remember, you use synthetic division here. I put a 1 in that backwards L. It's always the actual root itself. Then I have my coefficients. That's 1, -1, and -2. I bring down the first term. 1 times 1 is 1. I add. And of course, I'm not worried about the remainder. I'm only worried about those terms in front. And since it was an x squared to start with, I decreased 1, so it's going to be essentially 1x plus 0, which is just y equals x. Very good. What about, run out of colors, y-intercept?
0, -2. Or no, 0, 2.
0, -2?
No, just 2.
Just 2? Very good. Remember, you plug in 0 for all of your x's. That's how you get -2 over -1, which is a +2. What about my x-intercepts?
I got -2, 0, and 1, 0.
Close. Watch your sign. Remember, you have to set the numerator equal to 0. So that's going to be x minus 2 equals 0 and x plus 1 equals 0. So you have to still do the opposite. So then it's going to be not -2, 0, but 2, 0. And then -1, 0. That is how you find all your different properties of your rational functions.